This is a completely fair coin that is 50-50 heads or tails. If we toss it over and over, we end up with a stream like this one. Using this stream, let's play a game. You get to pick a pattern of 3 tosses, any of these 8, and take whichever one you like the look of. Let's say you go for triple heads. I get to go second, which means that I get to see your choice before I make mine. And knowing what you've picked, I'm going to take tails, heads, heads. Once we've decided on our patterns, we'll sit and watch the coin one toss at a time, and whichever of our 2 patterns ends up turning up first is the one that wins the game. In order for you to win, you need 3 heads in a row to appear, but unfortunately you got a tails instead of this third one. Letting the game continue, we end up here, and this pattern is mine, so I win this round. Running the game again, I've ended up winning a second time. Playing one more match, you take this game, and in particular, you've won via 3 heads right off of the start of the game. This particular case is quite important, and we'll get back onto this later, so just keep this in the back of your head for now. Now overall, obviously 3 games doesn't really tell us much about who's more likely to win, so let's repeat this 80 times. Letting these games finish, the final score is 69-11. This distribution cannot be attributed to luck. If we were to run this game forever, the exact odds would trickle down towards 7-1 in my favor. Which ought to bother you, because thinking about it, why would any pattern of 3 coins be more likely to appear than the other? There's nothing unfair about the coin itself. There is, however, apparently something extremely unfair about the patterns that emerge. So the question is then, where does our intuition break down? Because obviously the 1 in 8 that we're thinking of seems pretty reasonable. But as it turns out, there is one important part of the game that ends up completely changing this. Let's think about it like this. If we chop the stream into separate groups of 3, no group ever shares a coin with its neighbor. I'll also sort these each one by one to see which of the 8 patterns it happens to be. If we imagine 48 more groups of 3 and then divide them across our 8 bins, they'd fill up at more or less the same rate. And this is what we think of when we say 1 in 8. In separate groups of 3, no individual pattern has an advantage over the other. However, in this game, we do not chop the stream up like that. We read every 3 toss in a row, including all the ones that might sit at a boundary. So this means that rather than discarding coins that could have formed a pattern, we end up allowing them to proceed. And as it turns out, there are a lot of boundaries. 18 tosses would give us 6 separate groups if we divided them into 3s. However, if we allow overlaps, we end up with 16 overlapping windows. So then, why should any of that make a difference? Well, let's suppose you're scanning along a stream like this one and you spot a run of 3 heads somewhere in the middle. And let's also suppose that this is the first time 3 heads have shown up. If we take a step back from the run itself, let's try and find out what the coin in front of it could be. If we consider head, then we'd end up with 4 heads in a row, which would mean that the 3 heads had already finished one place earlier back here. And we just said that this was the first time, so that can't be it. This obviously leaves us with tails, and if we look at the pattern that this forms, it forms a tail and then 2 heads, which is my pattern, which, as it turns out, has finished a full turn before yours. For the most part, there's nothing in this argument that depends on where in the stream we're looking at. so it covers almost every instance except one special case, which is the case where the 3 heads appears right at the very beginning. If there are 3 heads there, then there's no coin before it. And so considering this, the likelihood that you get 3 heads in a row would happen 1 in 8, which is that ratio that I had mentioned at the start. And so that's the entire thing. You win the 8th of games that open with 3 heads, and I win the other 7. If you're wondering where I got tails, heads, heads, I didn't pull it completely out of thin air. There is a recipe, and thankfully it's short enough that you can learn it in your head if you wanted to show this off at a party. What we do is we take whatever your opponent has just committed to, so this is already assuming that you're going second. Then you copy its first 2 symbols onto the end of yours, take the second symbol one more time, and then we'll turn it over and stick it on the front. So for example, we might convert heads, tail, heads into heads, heads, tails. Now, if we compare that process against all possible openings, we end up with this board. And I'd like to point out that every single one of them has an answer that wins more often than it loses. Even the weakest reply anywhere on here still wins 2 games out of every 3. Out of all of this, however, there is also one special case, which is when you're going up against heads, heads, tails. According to the recipe, we might convert this to heads, 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 because it just seems like we're getting to the same point 1 step sooner, so surely that would have to be better, right? But it turns out it isn't. You see, those 2 are exactly half and half in terms of their likelihood to win, and you've just given away your entire advantage for basically no reason at all. Because if we just blindly respond with heads, 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 we know from our original example that tails, heads, heads would be superior to that argument. If we take all 8 patterns and put them on a ring, we can draw an arrow from each winning pattern to the one that it beats, one of which we found already. Once we've drawn the rest of them, we find that every single pattern on this ring has an arrow pointing straight at it, which is another way of saying there is nothing at all that you can open with that doesn't have a counter. This raises an obvious question then. If some patterns are stronger than others, then surely one of them has to be the strongest. In that case, let's take 4 patterns and try to line them up in order. Looking at them, at first glance, everything seems orderly because technically all the arrows are pointing in the same direction. When we check the last pair, however, we spot a divergence. Tails, tails, heads beats tails, heads, heads, which is the pattern at the start of this loop. And so we discover that the ordering closes in on itself. If you think of a game like rock, paper, scissors, you know that being strong against one opponent doesn't tell us anything at all about being strong against another. And so we end up discovering that the shape of this game is very comparable to rock, paper, scissors, and that it's essentially a circle. Once we understand this, we can recognize that going second is incredibly valuable. The first player has to commit to any position that they've chosen here, and the second player can then observe the decision they've made and then pick the appropriate counter. One question we might have is, while a match is still ongoing and we're waiting for either of the 2 patterns to appear, how much of what has already happened in the stream do we actually need to remember? Technically, the stream could run indefinitely, so at first thought we might think we need to remember all of it, but in actuality there's not very much that we need to remember. You see, out of that entire history, the only part that could still possibly matter is the tail end of it, by which I mean the longest run at the end that could still grow into one of our 2 patterns. Here, the last 2 tosses are a tail and then a head. And since tails heads is how my pattern begins, that much would be important for me to remember. Everything else that we've seen is no longer relevant. Across our 2 patterns, there are only then 5 tail ends that are worth remembering. Nothing at all, i.e. when the game has just started, a head, two heads, a tail, and then a tail head. If we consider adding the two winning patterns, then really the amount that we need to keep track of is very, very limited. Here I've drawn a path reader that we can use to imagine a series of tosses. Following this sequence, if we went heads, heads, tails, we would note that the two heads of progress that we'd made prior are no longer relevant. But rather than the reader going back to the beginning, it moves down to the tail node. And that's because the tail node is itself the first symbol of my pattern. If we were to get tails 2 more times, the reader would remain on that node. After getting 2 heads in a row, the match is over. Overall then, despite having a potentially infinite past, the only thing that really matters can be described in just a few nodes. We can take advantage of the reader in another way, as it doesn't only illustrate how the game might progress, but it can also be used to tell us who is more likely to win. Beside each circle, let's write down the chance that you, the first player, end up winning from that position. At the 2 finished patterns, there's obviously nothing to work out. It's either a 1 at your winning pattern or a 0 a minus. If we have a look at the bottom half of the diagram, we can observe something really interesting. You see, once the reader is sitting on tails, every single edge leaving it goes back to tails or across to tail heads or straight into my winning pattern. And there is no way whatsoever where that can climb back up to your winning path. So from anywhere inside that pair, your chance of winning is 0. If you'd rather see it algebraically, the 2 first step equations close in on each other until both values are forced down to 0 anyway. From 2 heads, a head finishes your pattern while a tail drops you down into nothing. So in other words, there's a 50% chance. From a single head, it's a quarter. And from an empty star, it's half of a quarter. This equation that we end up with is the same answer that we got about the argument about a single tail, except it's derived entirely through counting the transitions between these nodes. We can also use the same reader to try and estimate how long a game might take to complete, which, for reference, is a materially different question from who ends up winning. All we change is what the numbers are actually counting. From tails heads, another head would end on my winning pattern on the very next toss, while a tail knocks us back down to a single. So the value sitting there is 1 plus whatever happens afterwards. Working that back through the circles and from the empty start, we get 7. A race between these 2 patterns lasts 7 tosses on average. If we simulate these across 40,000 games, we can see a comparable conclusion. The distribution, however, is very badly lopsided, as roughly a quarter of all games are finished on the 3rd toss, but the mean lands right on 7. The reason that it's important making a distinction between what this tells us is that the pattern that tends to show up sooner doesn't necessarily mean it'll be more likely to win the actual game. The conclusion that we've reached about the 1 in 7 odds can also be obtained through a completely different manner, and this method doesn't involve discussing probability in any way. Here we can write out a pattern twice, one copy above the other, and slide the lower copy to the right one place at a time. At each position, we're only going to look at the parts that still overlap, and we ask ourselves, does every exposed pair match? We write down a 1 if it does, a 0 if it doesn't, and then read those 3 digits off as a binary number. 3 heads against itself matches at every shift, obviously because a run of heads looks exactly the same no matter how far along you slide it. So in this case, we get a 1, 1, 1, which read as a binary number is 7. Tails, heads, heads is the exact opposite. It only agrees when the 2 copies are sitting precisely on top of one another, and every other shift immediately mismatches. as a binary number that amounts to 4. This is a much more interesting pair, which is the end of one pattern against the start of the other. No suffix of 3 heads begins tails, heads, heads, so nothing matches anywhere at all, and we end up with 0. But 2 suffixes of tails, heads, heads do begin with 3 heads, so that one ends up coming out as 3. Here we end up with these 4 numbers, and the 2 that are sitting on the diagonal are the ones that we need to watch out for, because they measure how readily a pattern can rebuild itself out of its own near misses. 7 for the run of heads, and 4 for mine. And that gap, as it turns out, is the entire asymmetry we've been trying to measure this entire time. We can use Conway's formula to take those 4 numbers and then turn them into odds. The 2 diagonal entries are the self-overlaps, and they're the leading terms on each side, which measures how easily that pattern can rebuild itself. The off-diagonal entries then get subtracted away from those, and what they're measuring is something slightly different, specifically how readily a near miss on one pattern ends up handing the other one a finished copy for free. So let's substitute 4 minus 3 over 7 minus 0, which gives us 1 to 7. The odds of 1 to 7 means a probability of 1/8 against 7/8, which is now the 3rd time that identical ratio has appeared. 3 completely different pieces of mathematics that gives us the exact same rational number. Based on the ways that we've been able to derive these ratios then, there is one particular case that I want to discuss in a little bit more detail, and it's specifically around the counter pattern to 3 heads and heads, heads, tails. Both of them can be countered by tails, heads, heads. It's interesting because these 2 openings are not remotely equally easy to beat. Against triple heads, the counter wins on average 7 and 8, while against heads, heads, tails, it only manages 3 and 4. So what's going on here? Well, if we set 2 grids side by side, 3 of the 4 numbers turn out to be identical, and the only thing that moves at all is the self-overlap of the first player's own pattern. 3 heads results in 7 because it overlaps itself at every shift. Heads, heads, tails scores 4 because it has no self-overlap whatsoever. That final tail at the end negates every partial match it could have otherwise had. Swap the 4 in where the 7 was, and the odds shift from 1 in 7 to 1 in 3. 3/4 instead of 7/8. So there's a rule of thumb that's worth remembering, and that it's the more easily a pattern can rebuild itself out of its own failed attempts, the more exposed it is. And a long run of the same symbol is the most self-overlapping thing that you could possibly pick, which is also precisely why it is the worst thing you could pick. A pattern length of 3, however, isn't the only way that this game can be played. I don't want to also pretend that the rule that I gave you earlier about flipping coins to think of a counter would always work. For a pattern of any length, the best response generally has the same shape. Drop the last symbol, keep everything else in order, and put one new symbol on the front. So in practice, there are only ever 2 candidates for us to check, one led by a head and one led by a tail. But which of these should we check? Well, for heads, tails, heads, heads, our length 3 trick tells you to lead with a head, and that counter wins 3 times in 5, whereas the other candidate wins 9 in 14. This means our short rule ends up picking the wrong one. The reason is that it's really a special case for a pattern of 3, rather than a general law that we can apply to an arbitrary length patterns of this game. At longer lengths, the leading coin we choose has to come out of the whole overlap structure, and Conway's formula can actually be used to determine the optimal choice, so that would probably be the wiser tool to go with. What doesn't change, however, is what the worst option to pick is. Choosing a pattern of the same symbol across any length remains the worst possible opening we can choose. And it gets progressively worse the longer the pattern is, because it can still only win by turning up on the very first toss. Suppose you have to go first, but you're allowed to think about it carefully beforehand. How much of the disadvantage can you actually avoid with careful planning? And can you even stand a chance of winning at all? In order to answer that, let's look back at every opening we could make along with the best that the second player could take against us. 3 heads and 3 tails are obviously the worst, but 4 of the 8 are as good as it gets. Against each of those, the very best counter available still only wins 2 games in 3. Despite the fact that this is a real improvement, unfortunately it is still not a fair game. There is no opening anywhere on this chart that brings the orange line down to the halfway mark. And so the gap that we can see here is essentially what we're conceding for the privilege of playing first. So looking back at where we started with a single fair coin and 2 patterns. Across 80 races, we scored 69 to 11. And we've sourced that number from 3 completely separate explanations. The first was about a single toss, and how any run of 3 heads that isn't right at the very start has a tail sitting in front of it. The second was a state machine, where the only states we need to keep track of can be simplified to just 5 nodes. Whether we use linear equations or count, we can derive off of this that the transitions between them, when solved, give us 1/8. And lastly, the third way we've done it is through counting place-wise matching pairs. None of this is a trick of the coin. Every toss is still independently 50-50, and so if you stop the stream anywhere and try to guess the next 3 tosses, all 8 patterns would be just as likely as one another. They always were.